Good afternoon, everyone. Am I audible?
Yes, sir.
Yes, sir.
Okay. So we will continue with our yesterday's topic. So yesterday we were doing some example problems, right? Right. So the next topic of our discussion is going to be motional electromotive force, which is also called as motional EMF. Okay. So for this concept, what we are going to do is, let us say there is a magnetic field which is into the plane of the paper. I repeat, there is a magnetic field which is into the plane of the paper, and there is a metallic frame, which is frictionless in nature. Okay, on which there is a conductor PQ of length L that is placed. So there is a metallic conductor of length L that is placed, and this conductor is free to move on this frictionless frame. Okay. Suppose this conductor is given a speed v in the leftward direction. Okay, is given a velocity v in the leftward direction, which is constant. Clear? Now, let's say at the time of its start, it is at a distance x from one of the ends of the metallic frame. Then our job is to calculate. So first our job is to find out if there is going to be any EMF that will get induced. If at all an EMF is getting induced, what is going to be the value of it? That is what we are going to see. Okay. So let's get started with that. So how to proceed is, first, EMF will get generated only if there is a change of magnetic flux. So what is the value of flux here? So the magnetic flux in this case is going to be B into, where B is the magnetic field into the plane, into L into X, because it is BA cos theta, right? So B is B only. Area is going to be length into X into cos 0 degrees. So it is going to be BL into X. So that is the value of phi B. If you observe, phi is a function of X. Okay. When phi is a function of X, now if you differentiate on both the sides, if d phi B by dt is found, this will be equal to BL into dx divided by dt. Because B and L are constant, uniform magnetic field, and the length of the conductor is constant. Right. So BL into this dx by dt is what we can write it as V. Okay. Then what is d phi by dt according to Faraday's law? This is equal to the negative of EMF. So EMF is equal to B into L into V. Is it clear, guys? So if I take only the magnitude of EMF is equal to B into L into V, and this value is what is called as the motional EMF.
What is this motional, sir?
Because the conductor is moving. So this EMF is getting generated due to the motion of this conductor. That's why it's called as motional EMF. Okay. Is it clear, guys? Right. This is all about the concept of motional EMF in terms of its value. But here the important point is wherever you use the word EMF, we need to know the polarities of we need to know the polarities that are present at the ends of the conductor, right? So the conductor is of length PQ. Our job is to find which end is positive and which end is negative, which you people are going to do it now. Think and tell me. So what are the steps to be followed to apply Lenz's law? First, you need to find out which pole is north pole and which is south pole. Okay. Since the magnetic field is into the plane of the paper is acting like south pole and we are acting like the north pole. Accepted? Right. And the conductor is moving in such a way that the area is decreasing. When area is decreasing, what is going to happen to flux? When area is decreasing, what will happen to flux, guys?
Decrease.
Flux will also decrease. If flux is decreasing, what is the kind of polarity that will get generated? It will generate opposite pole. So this conductor is facing us. We are north pole. So what is the opposite pole that will get generated? It should be a south. So it should generate a south pole. Means the current is supposed to be in the clockwise direction. There is a mistake in my PDF, okay? Hopefully in your textbook it is given clockwise. If not, please change it immediately. So the current in the conductor will flow in the clockwise direction. From this, the important conclusion that we can draw is Q is positively charged and P is negatively charged because current is going to flow from higher to lower potential. Sharia? So since the current is going to flow from higher to lower potential, we can say Q is positively charged and P is negatively charged, and the current inside the conductor will be from P to Q. So please make a note of this point, guys.
Sir, I have a doubt, sir.
Tell me.
Your magnetic field is going inwards, right? In this case.
Yeah. Yeah. Paper
If
is
it's going outwards, it will change.
Yeah, it will change. Had the magnetic field been outward, then P would have been positively charged and Q would have been negatively charged.
Okay, sir.
Sir, on the open end of the conductor on the right hand side, it will be a north pole. So like the way we are
Sorry,
seeing.
can you please repeat the question?
From the side we are seeing it. I mean towards the right hand side, it will be a north pole, right?
From the side we are seeing it. Okay, means yourself, right? So you will act like north pole. Yes. Is that the question? I'm sorry if I didn't answer it properly.
Yes, sir. It is like that. But I was thinking if it is from the right hand side from the M and that part.
Okay. It is not. We are not seeing from right or something. You are actually you're writing on a paper, right? You're let's say you're sitting and you're writing on the paper and you're putting an into mark. Then by default, paper is taken as south pole, and the paper is facing you, and you're facing the paper, right? So when paper is going to be the south pole, you will act like north pole. That is what I meant. So this opposite pole is there, no? This opposite pole of what you are, not what the paper is. So since you are acting like north pole, there will be a south pole that will get generated.
Okay, sir.
Okay. Yeah. Had, see, for example, had like how Rohan asked, had, okay, I'll draw it separately. You guys think about it. Had the magnetic field been like this, okay, I'm changing everything. And let's say the same conductor PQ is there. Instead of moving to the left, let's assume it is moving to the right. Okay. So the magnetic field, what I'm doing is I'm drawing a set of dots. So what do we mean by dots?
North pole.
Which one is North Pole? The paper is acting like North Pole and you're acting like South Pole. Okay. So that should be fixed in the mind first. So what is the first step? The first step is see, these are all the steps you need to follow wherever you are applying Lenz's law. First step, identify what pole you are. Okay. First step. Second, check if flux is increasing or decreasing. In this context, what is happening? Flux is. So when the conductor is moving away from this fixed end, what is going to happen to the flux?
Area increases.
Area increases. So flux also increases. I hope the second step is clear. The third step is, if flux is increasing, then you have to write the same pole as you are. If flux is decreasing, then you have to write the opposite pole as whatever you are. Okay, in this case, since flux is increasing, same polarity, you're acting like which pole?
South pole.
South pole, no? So here also, you will be, the paper will also show you South pole only. Meaning, in this context also, the current is going to flow in the clockwise direction only. But what is the difference? Though I change the direction of magnetic field, why didn't the polarities get changed? Means, still Q is positive and P is negative. There is one more reason why the polarities didn't change. Let me see if you guys are able to apply the logic. Guys, it's a simple thing. You observe the changes that I made with respect to the textbook. Have this diagram in your mind. Have this in your mind. Check what is the difference.
Could you show the diagram once again?
What is the difference, guys? Though I change the direction of magnetic field, I also change the direction in which the conductor is moving. There, the area was decreasing. No, conductor is moving towards the fixed end. Here, the conductor is moving away from the fixed end. That is the reason why the polarities are still the same. But are these steps clear for you guys?
Yes, sir. Clear, sir.
Yeah, that is important. I suggest everyone to make a note. These are the only steps that you need to follow to apply Lenz's law, nothing else. You need not think anything outside the box, okay? These are all fixed. Okay.
Sir, when will the polarity change, sir?
I'll keep it. Now you guys try and see. I change the
North pole, sir. Current will flow anti-clockwise.
Current will flow anti-clockwise. Means P will become positive and Q will become negative. Clear? So there are two things. You need to look at the direction of conductor also. Okay, anyways, you do not memorize it. That is the thing I'm trying to say. In the exam, they change the direction of everything. Then you should be in a position to answer. Am I clear with this? This kind of a question might come. They might ask you which polarity. They'll give you options. MCQs, no. P positive, Q negative, P negative, Q positive. Obviously, it should be between these two. Then they can give both negative, both positive, just to confuse you. Okay, see both P negative, Q negative, and D is P negative, positive, Q positive. Just to, obviously, C and D are not possible. Since options are to be created, they can do it. So it should be between A and B. Okay.
So if area is decreasing, Q will be negative, sir.
Yeah, Q will be negative and P will be positive. Okay. So there are 4 permutations and combinations possible, depending on what are all the things are there. So whether the field is into the plane or out of the plane. Okay. Anyways, what I'm going to do is I'm going to give you a different logic to find the polarities. Okay. This is actually easier according to me. See if you guys can apply this also. An alternate way to find polarities of the ends of conductor. Okay. Now see, there's a conductor. This end is P, this end is Q. So inside a conductor, you have free electrons. So if I take an electron and let's say the conductor in the context given is moving to the leftward direction and the magnetic field is into the plane. See, guys, I again went to the textbook diagram. Okay. Don't get confused with this diagram. This diagram is only for you guys to understand. But now I went to the textbook diagram. So according to textbook, the magnetic field is inside. The conductor is moving in the leftward direction. And the electron is not shown to us. But we know the fact that metallic conductors will have electrons present in them. So what is going to be the force experienced by the electron? Is it not going to be equal to minus E into V vector cross B vector? Right? Minus E into V vector cross B vector. So minus E into, what is the value of V vector, guys? It is V in the direction of minus I cap cross B in the direction of minus K cap. Am I clear with this? So I'm taking out all the magnitude parts, EVB with a minus sign, minus I cap cross minus K cap is same as I cap cross K cap. So this will be equal to minus EVB into what is I cross K?
Negative, sir. Negative J, sir. Minus J.
Yes, minus J. That's right. So minus J. So minus and minus will get multiplied. EVB into J cap. So the meaning of this is, if one electron is experiencing a force in the direction of J cap, the remaining electrons will also experience the force in the same direction, J cap. Means all these electrons will experience a force like this and they will start getting concentrated at the top end of the conductor, as a result of which there is more amount of negative charge that is getting accumulated at point P and leaving the point Q to be positive. Is it clear? So this is another way to find. We got the same logic, right? Whether you use Lenz's law or this thing, it is giving you the same logic. Okay. So that is why the end Q is positive and the end P is negative.
Could you go up a bit?
Done?
Yes, sir.
Okay. So this is all about the motional EMF when the conductor is in linear motion. Okay. So the next type of condition that you can have is what will happen when the conductor is in circular motion. Okay, so what is the meaning is, instead of having a rectangular metallic frame, let's say if you have a circular metallic ring, okay, and instead of having the conductor PQ moving along a linear path, what if the conductor PQ was moving in a circular path with one of the ends fixed? That's what we are going to see now. Shall we get started? Now see. Read the question. There is a metallic rod of 1 meter length, which is rotated with a frequency of 50 revolutions per second. So 50 revolutions per second, with one end hinged at the center and the other at the circumference of the circular metallic ring of radius 1 meter, about an axis passing through the center and perpendicular to the plane of the ring. There is a constant and uniform magnetic field of value 1 Tesla, which is parallel to the axis which is present. What is the EMF between the center and the metallic ring? So how to solve this? See, what we need to do is, this end O is there, which is fixed, and P is the one which is actually moving. Okay. And let's say the metallic ring is moving with a constant angular velocity omega. And in time T, let's say it has swept an angle theta with respect to its initial position. Okay. And the radius of this metallic ring is R, and the radius of the metallic ring is exactly the length of this rod, which is 1 meter. Okay. Now, what is going to happen is, our job is to find what is the value of flux that is getting generated in time t. So flux is given as B into A into cos theta. And I've told you many times, they've told it clearly that magnetic field is parallel to the axis. Here axis is in the direction of the area vector, because axis is also into the plane. Okay, that is what they mentioned. No? About an axis passing through the center and perpendicular to the plane of the ring. So axis is also into the plane. Hence, you can say theta is 0 degrees. So what will be the value of flux? Flux will be equal to B into A. But here, B is also constant. But what is changing? It is the area that is getting swept at every instant is changing. Right? So how to find the area? If I take this as the first equation, the formula for area that I'm going to use here, there is no formula as such. I'm going to use the logic here. When the revolution is 2 pi radians, what is the equivalent area swept? Is it not pi r square? So when the complete revolution is taking place, that is for 2 pi radians, the area swept is pi r square. If the angle swept is only theta, then what is going to be the area? So it is going to be theta divided by 2 pi into pi r square. So pi and pi will get cancelled. It is half into r square into theta. Let me call this as 2, and that is 1. So flux will be equal to what? B into half into r square theta. B is equal to, sorry, B into half into r square theta. Then, okay, one thing to be kept in your mind is this theta is different from this theta. So what I will do is, I will take this as alpha. Okay, half r square theta. So differentiating both the sides, you get d phi by dt is equal to d by 2 into r square into d theta divided by dt. So what is d phi divided by dt? That is the EMF is equal to d r square by 2 into, what is the rate of change of angular displacement? It is angular velocity. So half d r square omega will be the EMF that you get generated when the metallic rod is in circular motion. So it is half d r square omega.
Sir,
Tell me.
sir, could you explain the theta alone, sir? That theta by 2 pi into r square, pi r square.
Okay, 2 pi radians means one complete revolution, 360 degrees revolution. But here angles should be measured in terms of radian, okay? So 2 pi radian will cover an area of pi r square. But when the metallic rod, observe the diagram now. But when the metallic rod has swept an angle theta, then how much is going to be this area is what I calculate. If I call that area as A, then area, so you need to cross multiply, right? It is unitary method. So theta into pi r square is equal to area into 2 pi. So area will be equal to theta divided by 2 pi into pi r square. Pi and pi will get cancelled. Theta by 2 into r square is the area.
Okay,
That's
sir. Understood.
Sure. So going forward, what you can do is you can remember this as a formula. Half into b r square omega can be remembered as a formula. And we know that omega is equal to 2 pi f, right? So we know that omega is equal to 2 pi by t, or it is also equal to 2 pi into f. Take these values and substitute it here. That will be the answer.
So 1 second, could you show the diagram?
Diagram. No? So,
In the diagram where theta is given, it should be alpha according to derivation, right?
alpha is the angle. So here, according to the, it's not a derivation, it's a problem actually. Alpha is angle between B vector and A vector. Okay. But since here we have taken this angle swept as theta, that angle is what I use to calculate the area. Okay. So theta is different and alpha is different. I hope you could understand it.
Yes, I understood.
Okay. Okay. Next. The next one is, there is a wheel which has 10 metallic spokes. So there is a wheel which has 10 metallic spokes. You know what is a metallic spoke, right? You would have seen cycle wheels. So something like this. Okay. I just do it randomly. I didn't count how many are there. So I will call the center as O and the outer end as P. Okay. So the radius of each spoke 0. Okay. The wheel has 10 metallic spokes, each 0.5 meter long. So radius is 0.5 meter, is rotated with a speed of 120 revolutions per minute. See, though the word speed is used here they are talking about the frequency. Frequency is 120 revolutions per minute or 2 revolutions per second. That is where you need to be careful. 120 revolutions per minute or 2 revolutions per second in a plane normal to the horizontal component of the magnetic field He at that place. So the magnetic field is given as 0.4 Gauss So this can also be written as 0.4 into 10 power minus 4 Tesla. Is 0.4 into 10 power minus 4 Tesla. What is the induced EMF between the axle and the rim of the wheel? What is the induced EMF between the axle, that is the axis, between points O and P? So induced EMF is half B R square omega. Okay. So half into B is how much? 0.4 into 10 power minus 4 into, what is the value of R? It is half. 0.5 meter, no? So half square into omega. So F is 2. Omega will be how much? Omega is equal to 2 pi into F. No, that will be 4 pi. So it will be 4 pi. Calculate everything. You will get the answer as 6.28 into 10 power minus 5 volt. Okay. So this will be the answer. And you know what is one of the common mistake that happens? Since there are 10 spokes, what people think is you need to multiply the 6.28 with 10 to get the final answer. But the answer is no, you need not multiply, because whatever is going to be the EMF between the point O and P will be the same EMF between point O and P dash, O and Q, O and R, because everything is connected in parallel. So you're able to understand. So if you calculate the EMF between the axle and one end of the rod, that is more than sufficient, because it is going to be the same value of EMF across all other devices also. Okay. Next. So energy consideration, a quantitative study. Now see, we took this conductor PQ, right? You had a metallic frame, you took the conductor PQ. Let's say small r is the resistance of the movable arm PQ of the rectangular conductor shown in figure 6.10. We assume that the remaining arms QR, RS, and SP have negligible resistances compared to QR, SP. Okay. QR, RS, and SP have negligible resistance compared to PQ. Okay. So what will happen to the overall resistance of this network? What will be the overall resistance of this network? Is it not going to be the resistance of PQ itself? That is R. Okay. Now what will happen is, when this PQ is moved, there is an EMF induced. So what is the value of EMF that is getting induced? EMF is BLV. So what is going to be the current that will get induced is it not going to be equal to BLV divided by smaller? So this is the first point to be noted. So there can be a question asking you, what is the value of the current that is flowing through the circuit? It is going to be V into L into V divided by R. Next. Since there is current flowing through this conductor, I repeat, since there is current flowing through this conductor, and this conductor is already present in external magnetic field, due to its own current, it will start experiencing a force of value I into L into B sin theta. Right? You guys remember this formula? So when a current carrying conductor is placed in external magnetic field, we know the fact that it starts experiencing force of the value BIL sin theta. So force in this case will be I into L into B sine theta. So F is equal to I into, what is the value of L, guys? Sorry. F is equal to, in the place of I will write it as BLB divided by R into, the length is L and B is B only. And sine of theta is going to be 90 degrees. Right. So this will be B square L square V the whole divided by R. So this will be the force experienced by the current carrying conductor. Okay, it will experience a force of B square L square V the whole divided by R. So sometimes in questions, how they will ask is, what is the force that we need to apply to ensure that the conductor is moving with a constant velocity? Okay. So EMF is going to be V into L into V only when it is going to move with a constant velocity. If it is going to change at every instant, then the value of V will also keep changing at every instant. Now, what is the force with which we need to apply to maintain a constant velocity? It is exactly the same value. So there are two types of questions that are possible. They can either ask you, what is the force experienced by the current carrying conductor? Yes, it is B square L square V divided by R. Or sometimes they can ask you a question, what is the force that is needed to ensure that it is moving with a constant velocity? That is also B square L square V the whole divided by R. Okay. Next, we need to calculate the amount of power that is required to ensure that the conductor is moving with this value. So we know that power is equal to force into velocity. That is one thing. Or you can write it as V into I, or you can write it as I square R or V square divided by R. If you write any of these values, you will get the same answer. So since in textbook they have used F into V, I will go with it. So power is equal to F is B square L square V the whole divided by R into the speed with which it is moving is V. So it will be B square L square V square the whole divided by R is the power. Okay. So B square L square V square the whole divided by R is going to be the power. Okay. Clear, guys?
So could you go?
Sure.
Done, sir.
Done? Okay. So this problem is important, but we will do it at the end. Or it's slightly confusing if I do it now. We'll do it at the end. Okay. So the next concept that I'm going to get started with, that we are going to get started with is inductance. So here, inductance is sometimes also referred to as self-inductance. Okay. So before I explain what this inductance is, we need to take the reference of this context from our previous chapter's knowledge. Okay. Listen. If there is a device like this, what do you call it as? Obviously, you call it as a resistor, and a resistor will have a value capital R associated with it. What is it called as? It's called as resistance. Similarly, you have a capacitor, right? So what is the property associated with the capacitor? It is capacitance, right? So OR generally stands for device and A and C stands for the property. In a similar context, if you have a device named as inductor, okay, then the property associated with the inductor is what we call it as inductance. Clear, guys? Okay, so that is what we are going to see now. For which we already know certain basics. Like, see, if there is a conductor, okay, I'll take it like this. Let us say you have a pickup coil. And you have an other coil, okay, which is connected to the battery. Okay. Now, as this coil is moved towards the pickup coil, what will happen? There will be a change of flux taking place. And due to the change of flux, what will happen? EMF is induced. Right? This is what is going to happen. This is a known fact. Right? Now, I have a question. What if the conductor is there and this conductor is connected to a battery with the help of a switch? What if the conductor is connected to the battery with the help of a switch? Okay. So when the switch is open, what will happen? When the switch is open, what is going to happen, guys? There is obviously no current, hence no change of flux. And what will happen? Hence there will be no induced EMF. Am I clear with this? Right, there is no current, hence there is no change of flux, and there will be no induced current as well. Now the question is, if I close the switch, what will happen? There is current, and due to current, there is an increase in flux from where? From this place, 0 to a steady state value. When that is happening, then there will be a flux change that is going to happen. Increase in flux is going to happen, after which there will be an EMF induced. Yes or no, guys? Right? This induced EMF is going to last for a very short duration. Right? Hence, can I say that there is an EMF induced due to its own current? Guys, are you able to understand what I'm trying to say? So in the previous case, what happened? The pickup coil had the EMF induced in it due to the change of current in some other coil which is in the neighborhood. Whereas in this case, what is going to happen? The change of the EMF is getting induced due to its own current. Correct? When this kind of a scenario, when this kind of a scenario is happening, this process is called as self-induction, means inducing EMF within itself, means additional, in addition to the already existing EMF, there will be another EMF generated. Okay, and this process is what we call it as self-induction. So there are three words that we have seen: inductor, inductance, and induction. Inductor is a device, inductance is a property, and induction is a process. So this is a process where an EMF is getting induced due to its own current. And if this kind of a process where the neighboring coil is able to generate EMF in the other coil, where this coil which is connected to the battery is called as the primary coil and the other one is called as the secondary coil. Okay, and this is called as the secondary coil. And this kind of a EMF induction process is what we call it as mutual induction. Clear, guys? This is what we call it as mutual induction. Clear?
Yes, sir.
Good. Okay. So once this is over, if you guys have made a note, I would like to stress on some important points. So can I say the total flux associated with a coil is directly proportional to the amount of current flowing through it? So total flux passing through a coil is directly proportional to current flowing through it. Can I say, guys? Okay. Now, if I remove the proportionality symbol, then N phi B will be equal to L into I, where this L is what is called as inductance, or as I told you, it is also called as self-inductance. Both have the same name. So N phi B will be equal to L into I. So from this, the important conclusion that I can draw is L is equal to N phi B the whole divided by I. Okay, where this SI unit is going to be something like this. N phi B is measured in Weber and I is measured in ampere. So Weber per ampere is also collectively called as Henry, Henry. So which is written here.
Sir, here N is the number of turns, sir, of the coil.
Yes, capital N stands for number of turns. So it is the number of turns of the coil.
What is WB, sir?
WB is Weber. Huh? That's the SI unit of flux, no? Forgot, huh?
Yes, sir. Yes, sir.
Sir, can you give a definition for inductance, sir?
Inductance, there is no definition as of now. There is no mathematical definition. I'll tell you the significance of it.
Okay, sir.
Okay. Right, this is one of the definitions. Now see, N phi B is equal to L into I is there, right? So differentiating with time on both sides, what do you get? D by dt of N into phi B will be equal to L into di divided by dt. Right, it will be equal to L into di divided by dt. So if I take that N out, N into d by dt of phi B will be equal to L into di divided by dt. Okay. So what is this thing, guys? Actually, I need not take the L out itself. So what is the derivative of flux with respect to time called as? Is this not equal to EMF?
Yes.
Right. So I've taken it as magnitude. Actually, it will be minus E. So E will be equal to minus L into di by dt, and magnitude of E will be equal to L into di by dt. From this, I can write L is equal to EMF divided by di by dt. Is that clear? Now, this is an alternate definition, alternate mathematical expression. Suppose in a problem, they have given you EMF and the rate of change of current, then you need to use this formula. Or sometimes if they're given you flux and current, then you have to use the first formula. So both are going to represent the same physical quantity called as inductance. Okay. Now, what is going to be the SI unit of it? SI unit is still Henry, but in this context, it is volt per ampere per second means volt second per ampere is what we call it as Henry. Okay. Volt second per ampere is what we call it as Henry. Okay. Make a note, guys. So L will be equal to magnitude of EMF divided by di by dt. Okay, listen. Now there are certain important things to be understood. First is, what is the symbol of inductor? So symbol of inductor is something like this. It looks something like a solenoid, but there is the symbol for inductor. Okay, this is first point to be. Secondly, there is another important note that we need to make. What is the significance of it? What is the significance of inductance? Okay. See, if I ask you what is Ohm's law, you guys will say R is equal to V divided by I, or V is equal to IR, right? From where we can write R is equal to V by I. So we can say R is inversely proportional to I accepted. So from this, what is that you can conclude, guys? You can say that the resistance will try to decrease the value of current in the circuit. So whenever there is a current which is flowing through, whenever you apply potential difference across the ends of a conductor, the resistance of that conductor will decrease the value of current in it. So R is inversely proportional to I. Accepted? First. Second is, if you observe inductance, L is equal to E divided by di by dt. So instead of R, you have inductance. Instead of voltage, you have EMF. Instead of current, you have di by dt. So can I say that inductance is inversely proportional to di by dt? Guys, this thing you will not find in textbook, so concentrate. So inductance is inversely proportional to di by dt means an inductor will oppose the rate of change of current. Okay, so an inductor will oppose the rate of change of current. So resistor will oppose the flow of current, whereas an inductor will oppose the rate of change of current. And this is the reason why inductor does not allow AC to pass through it. This you will learn in the next chapter. Does not allow AC to pass through it. Means it will not allow the alternating current to pass through it. It will only allow the direct current to pass through. Okay, this is an important significance. It is only for your knowledge to understand what does an inductor do. Okay, so have this in your mind. So with this, we have completed the basics of inductance. Okay. Next, what we are supposed to do is we need to see what is self-inductance value and mutual inductance value for solenoids, which we will see in the next class. Okay. Maximum by next Tuesday, this chapter will be over, or maximum by Wednesday. Next week, this chapter will be over. Then we can go to alternating currents. Clear, guys? So I suggest you all to go through this before the next class so that you will have a continuity of it. Okay, I hope you guys made a note of all these points.
Yes.
Right? Okay, then. I'll see you guys in the next class. And we can wind
Yes,
up.
sir.
Thank you, sir.
Thank you, sir.
Sir,
Tell me.
Sir, is it possible to purchase this chemistry study material, sir?
Yeah, you can do that. You can talk to ma'am. Okay, you just message ma'am about it. Go collect it. That's it. Okay.
Okay, sir. Thank you, sir.
She will give you the information about
Sir.
Okay, sir.
it. Okay.
Sir.
Who's this?
Sir.
Akshaya.
Sir,
Yeah. Tell.
Akshaya, sir.
Yeah, tell. 1 minute, ma. 1 minute.
Sir,
I'll
I
stop
had
the